Hi, and welcome to the first part of our section on Python Primer. In this section, we're going to take a look at some of the basic syntax and semantics of Python. If you need to get up to speed on the language, this is where we'll do that. We will be covering the basic syntax of Python. It's built in data structures, functions, classes, its standard library, and the new things in Python 3.5. This video primarily provides a basic understanding of the Python language constructs. If you feel you already have a solid grasp on Python, feel free to skip ahead. Python is a member of the C family of languages like C++ and Java, but Python is more of a distant cousin, as the designers of Python are quite happy to do things in a different way if it seems better. Still, if you're familiar with C or one of its descendant languages, you'll find Python relatively familiar. Let's get down to the nuts and bolts. A Python program is written as source code in one or more .py files and consists of statements and expressions. Both statements and expressions tell Python to do something. The difference is that expressions can be combined to form more complex expressions, while statements can be combined with expressions, but not with other statements. Python source code files are executed from top to bottom as soon as they're loaded by the Python runtime, which means that for simple programs, we could just write a series of statements in a .py file and then tell Python to run them. In this example, the if and else parts are statements, or a single statement with two parts. If you prefer to think of it that way, everything else is an expression. For more complex programs, we need a more structured approach. Like most programming languages, Python lets us create functions and classes in order to organize our code. If you don't know what functions and classes are, you could think of functions as miniature programs that could be used as building blocks for larger programs, and classes as combinations of functions, and data to create new kinds of data. We'll start with a brief look at functions. Functions are created using a def statement, which is a statement using the def keyword as its identifying component. As I said before, Python executes the statements in a .py file starting from the top. When it executes a def statement, the result is to create a function. That means that code that runs before the def statement does not see the function because it doesn't exist yet. The part of the def line inside parentheses is called the parameter list. It's a list of internal names for data values that are given to the function as input. Outside the function, those values might have different names or no name at all, but inside, they'll be stored in these variables. The indented block of code immediately after the def line is called the function body, and you could think of it as the source code of the function. The code inside the function body is an exception to the rule about running Python code from the top to the bottom of the file. That code is stored away and then executed later when we tell the function to run. Like the code in a file, the code in a function runs from top to bottom, one statement or expression at a time. If you're more familiar with C++ or Java, you may be wondering where the function parameter types and return types are. In Python, the data type is inherent in each data value, so the runtime always knows what type of data we're working with and whether what we're trying to do is a valid operation for that data type. Thus, for the most part, we don't need explicit data types. Python programmers sometimes talk about duck typing, which is a reference to the saying that if it quacks like a duck, it's probably a duck. What they mean by that is that if the operations we're trying to perform on a data value work, it doesn't really matter if it's precisely the kind of data we expected. It's probably close enough. If they don't work, Python will tell us what went wrong and where, which is often more useful to know than the kind of information that can be determined by comparing data types alone. For those situations where we do want or need to specify data types, we can use function annotations and the standard library typing module. Function decorators, which we'll discuss later in the course, can provide a convenient way of enforcing these annotations. The second major building block of a Python program is called a variable. A variable is pretty much just a box for storing a data value. The variable has a name, and we can use that name to access the data stored in the variable, or to replace the data with a new value. The function parameters in the previous examples were variables, as was the area. To set the data stored in a variable, we use an assignment section. This is a statement, so it can't be combined with any other statement. It gets a line of source code all for itself and the expressions that are part of it. An assignment statement consists of the variable's name on the left side of an equal symbol and the value we want to store in the variable on the right side. If the variable didn't already exist, it is created. Whether or not the variable existed before, the value is stored in the variable. Variables that are created inside a function are only visible inside that function, and each time the function runs, they are created anew. The last line of this example demonstrates that the variable created inside the function does not exist for code outside the function. It also shows what happens when we try to ask Python to do something impossible. It tells us what we did wrong and gives us information about where the problem occurred and how we got there. The third major building blocks of Python program are expressions. We've seen expressions in every example so far because it's nearly impossible to do anything without using expressions. Expressions consist of data values and operations to perform on those data values. The very simplest expressions are a single data value and no operations. For example, a single number. More complex expressions involve at least one operation and probably more data values as well. For example, adding two numbers. All expressions produce a resulting data value of some sort. Adding two numbers produces the sum as another number, while concatenating two text strings produces the concatenation as another text string. Using a variable name to look up the stored value is an expression. So is running a function. If the function doesn't explicitly return a value, a special value called none is the result. Anywhere we need a value, we can use any expression that produces the needed value. It doesn't matter whether the expression is a simple number like 55, or a variable name, or a complex combination of values and operators, or a function call, or any other expression. At least, it doesn't matter as far as the final result is concerned. Some expressions take less time to execute than others, so speed can be a factor. The final fundamental building block we're going to discuss here is classes. The word class is a synonym for category or type, in this case, referring to data values. A class defines a new kind of data value by describing a set of internal data and operations for that type of data value. This is done primarily by defining a group of functions that make up the class. A special function called _init_ is used to set up the internal data for a new data value of this type, and the rest of the functions define the operations on an existing data value of this type. All the functions of a class receive a parameter called self. That parameter is the data value being operated on. That's different from C++ or Java because while those languages do basically the same thing, the parameter is implicit instead of being an explicit part of the function's parameter list. Class functions, including _init_, should store and retrieve data from self when they want to manipulate the data value that they're connected to. Classes are support inheritance and multiple inheritance, but we're not going into that here. In this example, we've created a new data type called fruit, and then made two separate data values of that type. Then we use the anniversary function that we created as part of the class to modify each of them. Notice that the two instances maintain their internal variables with different values. Python has several flow control statements that will be familiar to people who know another language in the C family. For example, Python has loops and if, elif, else branches. Python also has a for loop statement, but it's not like the for loops in C, C++, or Java. Instead of counting through numbers, the for loop iterates through values. If we actually want to count through numbers with a for loop, that's easily done using a range. Iterate R. There's one last thing I should comment on before we wrap up this video, and that's Python's use of indentation to signify block structure. Most other programming languages have explicit symbols that mean beginning of a block and end of a block. However, it's a common practice in all of those languages to indent blocks, so humans find the code easier to read. In fact, failure to do so is often taken as a sign that a programmer is an amateur. That means that the block structure is actually represented in two different ways in most languages. By making the indentation into syntax, Python both removes that duplication and ensures that the code is readable. With that, we've come to the end of this video. In the next video, we'll look at some of Python's built-in data structures and data processing syntax.